What we have seen until now are radiation that are emitted in the visible region, where the electron ends in the second level of the hydrogen atom. However, other radiation can be detected in the ultraviolet region or in the infrared region. For example, when the electron ends in the first level or in the ground state of the energy level of the hydrogen, we get the Lyman series. This series corresponds to the ultraviolet region. The colored bright lines that we have detected in the visible region belong to the Balmer series that we have here, where the electron ends in the second energy level. For the infrared, we have the Paschen series, Bragg series, and Pfund series, where the electron ends in the third level, the fourth level, and the fifth level. So all these are radiation that are emitted by the hydrogen atom once it is energized. So all these are radiation that are observed with the hydrogen atoms in the different region of the electromagnetic radiation. Now let's talk about the absorption spectrum of the hydrogen atom. So here we repeat the same experiment, but we have a source of white light that passes through this vacuum tube that contains the hydrogen pure substance. And here, as the light passes through the prism, we have the same phenomenon, where the light is spread into different colors. However, what do we notice? We notice that there are black lines on the absorption spectrum. Here we have black lines instead of the colored ones that we have noticed in the emission spectrum. What happened here is that energy was absorbed at a specific wavelength from the hydrogen atoms. We can see here that in the absorption process, the electron moves from a lower energy level to a higher energy level. For example, here we have an electron that moves from the second energy level to the third energy level. And when the electron moves to a higher level, it means that it has absorbed energy in the form of a photon of energy h nu. Here we can see the two spectra. We have an emission spectrum and an absorption spectrum. We can see that both of them are the same. However, the first one we have colored bright lines, and the second one we have black lines. Here these black lines because the red color, or here the green color, were absorbed from the hydrogen atom. But here the hydrogen atoms emit these bright lines. So we can see here that any given element has both spectra, emission spectrum and absorption spectrum. Now let's talk about the emission spectrum of the hydrogen-like ions. These hydrogen-like ions are elements but with one electron. So they have only one electron. For example, the helium element, which has two electrons, so it is converted to an ion because one electron has been removed from this element. The same thing for the lithium, which has 3 electrons. So 2 electrons have been removed from the element to get the lithium plus 2. So these elements are called hydrogen-like ions because they have the same properties like the hydrogen. So the Bohr's model is also applied for this type of element. However, we make a small change because with the hydrogen atom, the energy of its electron is equal to minus RH times 1 over n square. But for the hydrogen-like ions, this one corresponds to the atomic number of the hydrogen. For the hydrogen-like ions, we replace this 1 by Z square. So we get this for the hydrogen-like ion. So it is the only parameter that is modified with these ions. Also, to determine the radius of the hydrogen atom, for the hydrogen, we know that the radius of the hydrogen atom is equal to A0 times n square. The A0 is the Bohr's radius, which is equal to 0.53 angstrom. But for the hydrogen-like ions, here again we have the radius, which is equal to A0 times n square over Z. And the same thing for the energy that is emitted during a transition. So we can write here that the energy for the transition of the electron is equal to RH times Z square 1 over n square initial minus 1 over n final square, which is also equal to the h nu, energy of one photon. We can write it like this, which is equal also to h times c over the wavelength of this photon. So we can write it like this: 1 over wavelength is equal to RH over here we have a Rydberg constant divided by the Planck's constant times the speed of light, which is also a universal constant. Here we have a constant which has this symbol. It is also the Rydberg constant with the value of 1097 times 10 to the power of the plus 7 meter negative 1. So here it is another way to write this relationship. But for the hydrogen ion, it is written like this. So we have to incorporate the atomic number of the hydrogen-like ion. Also, here we have to be careful. This, it corresponds to the initial state. So here we have to make sure that the Ni is smaller than Nf, either in absorption process or emission process. We have to make sure that to write first the smaller state and the larger one, in order to avoid the negative sign for the wavelength. Now we can do this example. Second, in the second example we have two questions. The first one, we have to calculate the energy in EV required to ionize from their ground state the ions helium plus and lithium plus 2. So here we have to determine the ionization energy that we will call I. Here we have the electron of the hydrogen or of the helium, which is in the ground state. Ground state, which means N is equal to 1. And when we talk about the ionization or the energy to ionize, it means the energy to remove this electron. So we have free electrons, which means that the final N is equivalent to infinity. To calculate this energy, we have this relation, which is equal to the energy required to ionize this electron. So this energy should be absorbed. So it is written like this: RH times the atomic number of helium. Here we have the initial state, and here we have the final state. So here we have 1 over 1 square minus 1 over n to infinity. This fraction is 0, and so we get this value to 10.6 eV. It is the value of the Rydberg's constant in eV times, because the atomic number of helium is 2. So here we replace by 2 square times 1 over 1 square. So which gives a value of 54.4 eV. So here is the energy that must be provided to ionize the helium atom. And we repeat the same thing with lithium. Lithium 2 plus. Here the energy needed to ionize the electron in the lithium 2 plus is equal to 13.6 electron volt times 3 square times 1 over 1 square, which is equal to 122.4 eV. Here is the energy to provide for the electron to be ionized. Here we can see that it is positive in both cases because it is absorbed. Now let's do the second question. What are the wavelengths in nanometer of the limit lines in the Paschen series for beryllium 3 plus? So here we have limit lines in the Paschen series. We have seen that in the Paschen series, we can go back here. So the Paschen series, the electron ends in the third energy level. So the limit here, we have the first transition, first limit. It corresponds to the transition between 4 to 3, and the second limit it corresponds to the transition between infinity and third level, because here we are in the Paschen series. So we use this relationship. We start by the first limit between 4 and 3. We know this relationship 1 over lambda, which is equal to Rydberg constant times z squared times 1 over n square 1 minus 1 over n2 square. Here we have to be careful. n1 must be smaller, or yes, smaller than n2 in order to get a wavelength that is positive. And here we have the z square, which is equivalent to 3 square or 4 square, because the beryllium, it has an atomic number which is equal to 4. So we have here 4 square. And here for the first one we have between 3 and 4. So we can replace here. So we get lambda, which is equal to, or by the value it's better, which is 1 times 10 to the negative or to the positive 7 meter negative 1 times 4 square times 1 over 3 square minus 1 over 4 square. And here we have to the negative 1. It is the inverse of all this value. And we get the wavelength of the first transition, which is equivalent to 117 nanometers. So here it's for the transition 3 to 4. Now for the second transition between 3 to infinity, the wavelength is easier to determine because we don't have this fraction. So it will we will write the same thing, but here it will get to 0. If we replace by the same values, we get here LH times z square times 1 over n square here for 3 minus 1 over n square infinity. Here all this fraction is 0, and we get a wavelength of 51.4 nanometers. So we can see that for the second limit it is lower in wavelength, which means that the energy is more important when we have to ionize an electron or an element. Now, as summary, we have seen that the electron in the Bohr model is allowed to occupy only certain orbits, which means that the energy of the electron in the hydrogen atom and the hydrogen-like ions is quantized. The same principle as the quantum theory from Max Planck. Also, the line spectra originates from the electron motion between these allowed circular orbits. We know also that during the emission process, the electron moves from the higher energy level to a lower energy level, and during the absorption process, it's the opposite. Also, we have seen that the Bohr model could also be applied to study the hydrogen-like ions, such as helium+, lithium-2+, beryllium-3+, and so forth. However, when we have to deal with atoms that have more than one electron, the Bohr model cannot be applied, and it cannot explain the emission spectra of polyelectronic atoms. So another model in this case will be needed to discuss this type of spectra, and that will be discussed later in this chapter.